So vectors and vector resolution. As we've learned before, a scalar is a quantity with size, that's a magnitude or numerical value only. Good examples are distance, speed, time, and there are other ones. A vector is a quantity with the size, but also direction. The examples that we've had are displacement, velocity, acceleration. There are other ones like force and momentum that will be coming up later in the semester or next semester that'll be as important. But the whole idea of vector is the idea we need to talk about here. We're going to be using, when we draw diagrams, we're going to be using arrows to represent vectors. The nice thing about arrows pictorially is that the length of the arrow will be proportional to the magnitude of the vector, or the size of the vector. Vectors that have a larger size we're going to draw longer. And they also have a direction. The arrowhead points in the direction of the vector, because direction is a very important aspect of the vector. So for example, we could have a vector, a displacement vector, which shows you, say, 5 meters north, or a vector that shows you 8 meters east. East will be to the right, west will be to the left, but 8 meters is longer than 5 meters, so I drew it longer. We're not going to measure these precisely, but just give you the idea that 8 meters is bigger than 5 meters. Velocity is another one. For example, you might be going 25 miles per hour or 25 meters per second. Let's say that's like northwest. Or you might be going 10 meters per second south. So those two vectors could represent that. And the comparable in length, the 10 meter per second south vector is shorter than the 25 meter per second northwest vector. When adding or combining vectors, or subtracting them, because subtracting is just adding a negative, but when combining, adding vectors, the answer is called the resultant. In force problems, in the next chapter, a couple chapters from now, we'll be doing force problems. The force vector, the resultant is called F net. We'll come back to that. But for example, you could have, say, a box sitting on a floor. If this represents a box sitting on a floor, and two people are pushing on it. One person is pushing with a force of, say, 13 newtons. Newtons will be our units for force, metric units. And then somebody else is pushing on it with a force of 10 newtons. What's the resulting force, the net force acting on that box? Well, it's just going to be 13 plus 10. So the net force, or the resultant, and we use usually a capital R for result. The resulting force will be 13 plus 10 is 23 newtons. And the direction here, which is important, is to the right. So the net force, the resulting force is 23 newtons to the right. What if you had the same box sitting on the floor, and there's a 10 newton, somebody's pushing with 10 newtons to the right, and there's an opposing person pushing on the other side with a stronger force. I drew that a little longer, 13 newtons to the left. What is the resulting force, the net force? Well, the resulting force here is 13 left minus 10 is 3 newtons to the left is the net force, the resulting combination of those two vectors. Here's another example at the bottom. Airplane, and here's my little sketch of an airplane in part A. This is supposed to be an airplane, not the number 4, but an airplane that on its own engine power can fly at 100 kilometers per hour. So that arrow represents how fast it can fly without any wind assistance. But let's say there's a tailwind, which is great when you're in an airplane or in a bike. It helps you. The way you can draw that 120 kilometer per hour tailwind is another vector that points to the right, but short, 20 kilometers per hour. So now we need to add these two vectors. So what's the net resulting velocity? Well, the resulting velocity, r, is 120 kilometers per hour. And to the right, when we're talking about airplanes and cars and maps, to the right is east. You could say to the right here, or you could say east. West is to the left. North is to the top of the page. But the resulting speed or velocity of this airplane is 120 kilometers east. But now in part B, here's part B, same airplane experiences a headwind. Once again, that's a real pain if you're on a bike or in any vehicle that slows you down, because if you're trying to make forward progress at 100 kilometers per hour, but the wind, a headwind, which is against you, is 30 kilometers per hour. Once again, the math is pretty easy here. The resulting speed of the airplane relative to the ground, the velocity, is 70 kilometers per hour. But he's still making forward progress, still traveling towards the east, but at a slower rate. So that would be our resulting speed. It's the combination of those two vectors.